here to talk about what needs to be done in the third tab in the Excel file that you need to submit by next week. So this is now, it says plot gain versus frequency, include error bars, and plot theoretical formula on top of the measured values. So the types of graphs that we always want you to fit in Physics 101 will be only the linear plot, the linear graph that you've done here in tab 2, where you can use linest, this function called linest, to trace what is the uncertainty of the slope and the y-intercept. So in Physics 3, we really want to go heavy on errors and tracing errors and doing error propagation and being careful with handling errors. So this can be done when you do linear fits because you use this function linest and you really trace the errors well. When we, however, have any other crazier function, so for instance, the function, what we're trying to plot here today is exactly this theoretical equation here. You see this says gain, this is the theoretical equation. You're going to plot gain, gain will be your vertical axis, against frequency, frequency will be your horizontal axis. So you see how this is not a linear equation. This is not a quadratic equation, this is not an exponential, this is not a polynomial, this is nothing, it is its own equation. So in Excel, you're not going to find a way to fit that. I mean, you can, if you use a polynomial of 10th order, you can fit anything in the world practically. I mean, the higher the order of a polynomial, you can fit anything. But is it meaningful? What every polynomial means? You don't know. So can you fit things? Yes, but is it meaningful? No. So besides the fact that this Excel does not have a fit for this equation, is the fact that even if you use Excel's polynomial or exponential fit, it doesn't give you a good way to handle the errors of the fit, okay? So only the linear fit is where we have a good way to handle the errors of a fit. So that's why we are going to, even when we have a log plot in the future in exponential decay, we're going to linearize that plot first, mathematically, linearize the data table, and then plot the linearized plot, the linearized data, okay? So that we are examining a linear fit and then tracing the errors of slope and y-intercept. So here, however, what do you do when you made a graph and the graph cannot be linearized easily, and so you cannot fit? So what can you do to still analyze the data set that is not a linearizable plot, or not a linear? What you can do is you can plot the theoretical formula. So what you can do is to plot the theoretical formula, okay? So that's what is interesting here, and that's what this exercise is all about. So it's not a fit, it's what it should have been if it was theoretical. Okay, so let's do this. The first thing we need to plot is frequency versus gain, okay? So you can like select the tables, right? Select these are the measured gain and the frequency. Oh boy, it's a long data table here. There may be cleverer ways to do this, but I just selected it all. And you guys are using different, I'm using a Mac, you guys are using this somewhere else, so you go in Windows, your menu is going to be somewhere else, okay? So here we go, we got our initial fit. So this you can say is, you always put a chart title, right? Gain versus frequency, etc. Always insert X and Y labels. I'm going to be lazy here, you know the drill. And gain, what is gain here? Gain is a quantity that is division between two voltages. So gain does not have any unit. So you would just, in the vertical axis, say gain, no units. In the horizontal axis, you're going to say if the frequency has a unit, put the unit, right? Okay, so here we have our data points, and now we need to put the error bars for this data point. So make sure you insert the error bars. Again, I'm in Excel, on a Mac. So the way I do it, I go here, I say error bar, and I say put any error bar here. And then I finally see the menu. But you guys in Windows will have the plus symbol over here by the side of your chart area, and that's where all your menus are. So error bar should always be custom, right? Customize your error bar. And what is the error in the frequency? I think in this case, I don't want you to even insert any error in the frequency. So I'll say fixed, and I'll say 0001. I don't care. For frequency, I'm not giving you any error here. So you can actually, frequency normally will have an error that will be for us about 1%. So you know what? Let me just do like 1% error for the frequency. Done. Now we need to examine the vertical error, the gain, because that one we have. Okay, so let me click here. This is the rudimentary way in a Mac that I have to do this for Excel. So I click on the vertical error bars. So please, vertical error bars, please. It's only, oh, okay, vertical error bar. Very good. I got it. The menu here inactive. So what do we want the vertical error bars to be? We want, the vertical error bars to be the error of the gain. So I will say custom, specify, and the vertical error bars now will be the error of the gain. You come and click and drag. And remember, in the Physics Lab manual, you have a tutorial on how to use Excel, and you can also just Google how to insert error bars in Excel, etc. Okay, so done. That's the plus error bar positive, and then the negative, because error bars are bars that go up and down around the central point, right? And they will have the same value going up or down. All right, so here we go. We got a much better graph. Let me make it bigger, but not too big. Get this menu out. We're done with that. All right, so here we go. We got our graph, and these are measure points, and there they have their corresponding error. So as it says here, the next thing I need to do is to actually, I cannot fit this. There's no fit for this, but what I can do is plot the theoretical equation. So here's the theoretical equation for it. And there's something good. The reason why we're doing this is, well, there's a little trick in Excel that I can teach you about this, because what is this formula for the gain? Is 2 pi f, the frequency, right, times, so time, oh boy, 2 pi f, the frequency, and then a resistance times a capacitance. And again, you have the multiplication resistance and capacitance. So this, by the way, you don't need to know now the background of this, but this was a low pass RC filter. So we're collecting the measurement of the voltage, the input voltage and the output voltage passing through an RC circuit, okay, for different frequencies. So you are given, if you have a fixed resistor and a fixed capacitor, the thing that is changing is the frequency. So we're going to insert this theoretical formula here, but look at that. F in the formula will be changing, but R and C will have this fixed. I want to always read these fixed values and not change. So how do we insert this type of formula in Excel? We click on the first cell we want to, and we start with this equal sign, go to the formula bar to straight edit or there. So this is the formula we need to insert. So it's a division, and in the denominator there is a square root. So here is the numerator, and then I have then SQRT in the denominator, okay? All right, next, the numerator is going to be 2 times. How do you write pi in Excel? You write pi PI and then open and close parentheses. All this you have to do is PI and open and close parentheses. That's how you write pi in Excel. So there's nothing to put inside those parentheses. This is the way you write pi in Excel. So you will know how to get the value. And then multiply by f. So f is something that will change. We want the formula to adapt to different values of frequency. So just capture that cell address. And then times r. So r is going to be this, but I don't want it to change. I don't want the value of r to, when I drag this formula to the different cells, I don't want it to try to read the value of r in a cell below. I want it to be stuck always in this cell that has this address A8. So if you want to have a fixed cell address and not change, what you need to do is to put the dollar symbol in front of the column and in front of the row. So $A, $8. So that's what you need to do. That's what we just done. Multiply by, the next is C, the capacitance. So multiply by the capacitance. I also don't want the capacitance to change. So I'll do $B, $8. So this way we're fixing that formula. In the denominator, I have square root of 1 plus, and then I have something that is squared, right? And inside that square, I have again the same formula I had before. So 2 times pi times the frequency, I grab that again, times R times C, but now I go and insert the dollars, $8, $8, $B, $8, so that R and C are read constantly from the same place. Okay, so now, as usual, we're going to drag this formula to all the values here, right? 135 data points, well, 120 data points, I think we have. Okay, so now I want to plot this theoretical gain over here. I'm not asking you to produce any kind of uncertainty for that, okay? Sometimes we can do the uncertainty. So how do you do that? So now you go here on your graphical area. You guys will probably click on the plus symbol in your case, but I will go here, select data. Okay, so you have this option there also in Microsoft Windows, select data. So you select data, and now I want to insert a new data series. So series 1 is the frequency and the measured gain. I want to insert a new data series. So in here in a Mac, I will click on the symbol plus. For you, I think in Microsoft, in Windows, you have like a word add anyway. So I included series 2. So series 2 is now going to be the theoretical gain versus frequency. So what do I want the x values to be? Still the frequency. I'm going to plot against the frequency. So it's still the frequency. Okay. So I select all those values for the frequency. Done. Now what do I want now my y values to be for this second data series? I want them to be the theoretical gain. So go theoretical gain. Done. Okay, and we're good, and we say okay, and we plot. So let's go see our graph, and you see now plotted in this with this red little symbols. Okay, so this is the thing that you will be doing this in your labs this semester. Okay, there will be things where you're not going to fit. You're just going to plot the theoretical values. So in red, what we have is the theoretical values. I don't want them plotted as dots. This is very important. I don't want them plotted as dots. I want them plotted as a straight line. So you guys will use the plus, again, menu that you have here in the graphical area. So what do you do to change? Do you see those red dots? To change the red dots into a straight line, a fit, because a fit, it's not a fit, but a theoretical curve. Okay, how to, so select, says the red data set. Okay, in my case, I have to double click the red data set. And I go here where it says the color, the pink bucket here. And I go here when I say line. I want a line, I wanted a solid line, okay? and I want a solid line of, say, red color. I'm going to do a solid line of red color. And yeah, this is it. And then in the case of the marker, I'm going to say marker options. I'm going to say I want no marker. So the marker is the dots. Oh boy, we did this. We're doing this for the, and obviously this didn't work well. So because I hadn't selected the entire red data set, so I want the entire red data set. How can I do that? Did I? Okay, hold on. You guys probably are at home saying, Professor, you have to do this. Professor, you have to do that. Okay, marker options. I want no marker. Yeah, because I'm formatting just a data point. I don't want to format the data point. I want to format the entire data set. Series option. Very good. Now I got the series. Marker. Marker options. No. Line. Line options. Solid. Red. Da, da, da. Why didn't this work yet? I'm going to have to stop this video. So, you know, in Windows, you can do things better for this silly thing here. Okay. Oh, well. So I'll go back to this soon. So I prefer always that this is not a point, data points, that this is when it is the, so those of you who are thinking like, why not data points? Why don't I leave just data points? Here we go. We succeeded in making a straight line on just a little part of it. I'm having trouble in just selecting the entire series, even though here is all highlighted, to do that change. And this is just cumbersome here for me. Okay, we'll try that again later, but to change that into an entire straight line, solid collected line, instead of data points. Why is that? This case here is not as bad, but there will be other cases in the future where you won't have a lot of points, and then you have the theoretical points and the measured points, and it's hard to identify which is which. And some of you will use colors or different symbols, and it's still hard to, because you won't have a lot of data points, to figure out the patterns, okay? So that's why I need you to have a theoretical line connected to each other so that you identify better the patterns. We'll get to that soon. So continuing here. So now that I have this, how am I going to quantify the goodness of this agreement? How good is the agreement between the theory and the experimentation, right? So when you make a linear plot, Excel will give you the so-called R-squared value. And we tend to see, most students, a lot of people using Excel, use this R-squared value to classify how good the fit was done. So the R-squared value says that the closest the R-square is to 1, the better is the linear fit, okay? So I invite you to read, for instance, this website here that talks about how R-square is actually useless. So it's an ongoing argument, and then they have a very good point about it. R-square is complicated. So that in general, what we say to students in introductory level physics, because when you go on to do research and etc., you guys will learn a lot better ways to match graphs. For instance, there are a lot of other statistical tests to do to match data sets and etc. And that's what the tabs 4 and 5 here are talking about. It's different situations here where we're matching different data sets and not exactly, it's not exactly the case we have here, but there's something called, there are different tests to do this, not just R-square value, etc. And chi-square, minimization, chi-square values that you can use to talk about the goodness of a fit and etc. or a model. But for us in introductory physics, there are two things. So what we say to students is, okay, don't toss R-square completely out of the window. You can still mention it, have it plotted or show it, but don't trust only on it, okay? So therefore, the other statistical parameter you should be calculating is this RMSE, right? The root mean square error. And here we are teaching you how to calculate those things, okay? So when you have a fit that is not a straight line, Excel is not going to tell you what is R squared. Excel is not going to tell you where is RMSE. You have to calculate them. So here's how you calculate them, and we have here the little guidelines. So the first thing you need to do is to first get the average of all these y values, average of all your measured gains, okay? So let's do, this is going to be therefore the average gain here, and we can write as equal to, let Excel do for you, average. Excel has an average formula, so the average of all these values here, and get all your gain values here, okay? So then click enter, and Excel, close parentheses, and Excel will do to you. So out of all those values, this is the average gain. So we needed to use in this formula here. So we're going to calculate y, meaning the measured gain, minus the average measured gain, and square. That's what we need to do statistically in this part here. So this is going to be equal to it's something squared, right? We're going to square this, and what we're going to put here is y minus the average, which is this value. Now the average value is not going to change, so we'll put $, okay? And drag this all the way down to all your data points. So that's one first step. Next thing we need to do here is the square of the residual. So now it's y minus the theory, so equal to is also something that's going to be squared, and so it is the gain minus the theoretical gain. So the measured gain minus the theoretical gain, and that's squared, and that's it here. So let's drag this down, drag. Okay, and then once you have these things here, now you're going to do the sum of all of these. So sum of the squares total, so equal to, Excel also has the function sum, so you're going to sum all of these, okay? You know, it's exhausting to pull this down all the time. There is a better way somewhere. Equal to sum of, you sum all of these guys here, okay? And you put that in the table. Okay, so now this sum is called SSE, and this sum is called SST. So now to calculate the RMSE value is going to be the square root, so this is SQRT, of the SSE, so SSE is this, divided by the number of data points. I think we had, I don't even remember, I think we had 120 data points. I'm just going to put 120, we can check that later. How many data points we have? I mean, we can just select all of them, and then on the 121 it says count, see, on the bottom of Excel. So actually I would divide this by 121. And this is the R squared value. So the R squared value then is calculated as 1 minus, and now this division of, okay, this division of the SSE divided by the SST. And so we're done. Okay, so so this is, so read about the RMSE, read about the R squared and what they mean and when something is good. So RMSE being small is good, and RMSE has unit, is the unit of the gain, the same unit that the gain has, the vertical axis would have. And the R squared doesn't have any unit, but the closer to 1, that's in theory, well, which would be better. Okay, so you can then when you're making a lab about this more complicated graphs, well, graphs that are not linear, you can then insert a text box where you show then R squared. The R squared is then 0.88 here from my example, and the RMSE is going to be equal to 0.0, say 7 here, okay? Again, with the unit of the gain, which has no units here. But you can then in a graph show this a little bit better than what I done. Okay, I did this. It's anyway. Okay, back again to, so I think we're done with this. You guys, this is what you needed to do, and in the future, that's what you need to do in. So let me see if I can figure out how to, sometimes I was able to do that. Series option, primary axis, secondary axis, okay, format, no, I don't want the data point. Yeah, it looks like I have no idea how I can select. Let's see, select data. And series 2. And then I want to have a solid line. Okay, that was the series 2. So obviously selected the wrong series. So there we go. That's bad. So it selected the wrong series. Isn't that lovely? Select item. Series 2. What is series 2? Where did they select as series 2? Okay, that's time. Yeah, that's, I don't care about that. Yeah, that's theoretical, so that's exactly what I want. I want series 2, and then I say okay. Oh boy. I really want the series 2. And I'm back on format data point here. Yeah, I have trouble in selecting the entire series. I'm having trouble in selecting the entire series. It seems I can only select a few data points. See, here I selected an entire series. Oh, here we go. Oh boy. Solid line marker. Oh, I cannot believe finally it was done. So I'm sorry, I don't think you guys in Windows have as much trouble as I have, because you know, Excel for Mac doesn't have all the exactly the bells and whistles that it does have. So here you go. I need that to be a straight line. That's it, guys. Really need that to be a straight line, and it will be easier for you guys in Windows than it is for me. I just had to select the entire data series to do that. Okay, and it was a matter of normally. Okay, I'll tell you what normally you need to do. You just need to double click on points of that data series and eventually select the entire data series. If you double click, it says data series selected. And I don't know why it wasn't doing this now. And I really don't think I've done anything different. I just repeated several times and finally it worked. Anyway, good luck. That's what you need to do. Take care.